Imagine you're driving a car down a straight, smooth road. You keep the steering wheel steady, and everything goes perfectly. Now imagine the road starts to get a bit bumpy. Every time you hit a small bump or make a tiny adjustment to avoid a pothole, your car's direction changes just a little. At first, these changes seem small and unimportant, but as you keep driving, all those little bumps and adjustments start to add up. Before you know it, you're no longer on the straight road. Instead, you find yourself on a completely different path, heading in a direction you didn't plan. Those tiny changes in steering, which seemed insignificant at first, ended up leading to a big, unexpected change in your route. Chaos is a term we use to describe the uncertain and unpredictable parts of the universe. Often we are correct in doing so. Chaos shows how events can behave unpredictably, but there's more to it. There's a deep truth in how organized systems can become chaotic, and there's a simple beauty in how this happens in our seemingly predictable world. Chaos is unpredictable behavior that is very sensitive to small changes in conditions. The first significant discovery of chaos was made by Edward Lorenz in the 1960s. While studying weather patterns, he found that even tiny differences in initial conditions could lead to vastly different outcomes. His work showed that chaos is highly sensitive to starting conditions. No matter how close these starting points are, small changes can lead to completely different results, making the system unpredictable and hard to follow. This means that the future of chaotic systems can't be predicted accurately. If slight differences in the beginning can cause huge differences in the outcome, predicting the future becomes nearly impossible. Since we can't measure the exact starting conditions perfectly down to the smallest decimal, it becomes more difficult to forecast the future accurately as time goes on. This is the nature of chaos. Most people, when they envision chaos, see a myriad of phenomena intersecting and overlapping in berserk order. It is hard to envision chaos in a world that seemingly exudes order, but more often than not, chaos is found in the most unbelievable corners. Examples include our solar system itself, the motion of celestial bodies flinging out of orbit or colliding with others over time. This introduces the challenge known as the three-body problem in physics. It emerges when trying to forecast the movement of three celestial bodies influenced by their mutual gravitational pull. These bodies might be stars, planets, or any massive objects. The difficulty arises because the gravitational forces between them create a complex, dynamical system that's hard to solve analytically. Each star exerts gravitational force on the other two, causing them to move toward each other. Yet, as they shift positions, the gravitational forces acting on them change, setting off a feedback loop. This interaction means the movement of one star influences the motion of the other two, resulting in a dynamic and chaotic behavior among the celestial bodies. Even slight variations in their positions or velocities can result in vastly different trajectories. Other examples of chaotic systems are the double pendulum and the spread of diseases. Events spiraling into chaos may seem random because we often link randomness with unpredictability. However, chaos and randomness are not the same. Chaotic systems can appear random, but they are fundamentally different. Pure randomness doesn't depend on initial conditions and generally follows probability. For example, tossing a coin 1,000,000 times doesn't determine whether the next toss will be heads or tails. Each flip is independent of the previous ones, and the outcome, heads or tails, is governed solely by the inherent probabilities of the coin flip, 50% chance for heads and 50% chance for tails. No matter how many times you flip the coin or what the previous outcomes were, the probability of getting heads or tails remains the same for each toss. In contrast, chaotic systems are governed by deterministic processes sensitive to initial conditions. This sensitivity to initial conditions means that even small changes in the starting state can lead to drastically different outcomes, a characteristic known as sensitive dependence on initial conditions. This is somewhat true for random number generators in computers, which use a set algorithm to produce numbers. If the exact initial conditions are repeated, the same outcome will occur. This output isn't truly random, but is still chaotic. This highlights that in a mathematical world where initial conditions can be specified exactly, chaotic systems are deterministic. While randomness can come from deterministic processes, it's not strictly defined by it, whereas chaos is. Despite being deterministic, chaotic systems pose challenges. They often defy reliability, making even precise measurements of the current state useless for predicting the future. To understand the present state, continuous measurements are necessary. This makes predicting long-term behavior nearly impossible. For instance, weather forecasts, crucial for daily life, rely on predictions based on multiple initial conditions rather than just one. However, trying to predict beyond a month is almost as uncertain as guessing. We may regard the present state of the universe as the effect of its past and the cause of its future. An intellect that, at a certain moment, would know all forces that set nature in motion and all positions of all items of which nature is composed. If this intellect were also vast enough to submit these data to analysis, it would embrace in a single formula the movements of the greatest bodies of the universe and those of the tiniest atom. For such an intellect, nothing would be uncertain, and the future, just like the past, would be present before its eyes. This quote by Laplace, a French astronomer and mathematician, encapsulates the concept of determinism in the universe, stating that if we know the position and momentum of an object, we can predict its future based on the laws of physics. For instance, we can calculate the trajectory of a thrown ball or where it will land. In theory, if we apply this principle to every object in the universe, we could completely predict the future. This is Laplace envisioning an intellect with total knowledge of nature's forces and particle positions, capable of predicting the universe's future state with absolute certainty. This deterministic view suggests no room for randomness. Every event could be foreseen given initial conditions and natural laws. However, this concept of determinism has been challenged by the advent of quantum mechanics, which introduces inherent randomness at the microscopic level. Chaos theory introduced the idea of the butterfly effect. It suggests that small actions, like a butterfly flapping its wings in China, can have big consequences, like causing a storm in New York City. This happens because tiny actions can lead to a chain reaction of events, going against what we expect. You don't have to track butterflies and weather patterns to understand chaos. You can see it with something as simple as a pendulum. Chaos involves sensitive dependence on initial conditions. This means that even if you tried to recreate the butterfly experiment, you'd never get the exact same result because conditions are always changing. This discovery challenged scientists' ability to predict the future accurately, even before considering quantum mechanics. Consider a pendulum. It's described by two numbers: its position, where it is along its swing, and its momentum, its mass multiplied by its velocity. If you plot these numbers on a grid, position on the horizontal axis and momentum on the vertical, you'll see the pendulum's path. This grid is called the pendulum's phase space, and the path it traces is its phase space trajectory. Chaotic systems, such as the mixed master universe proposed by Charles Misner in the 1960s, is a hypothetical cosmological model that describes a chaotic and dynamic scenario for the early universe. In this model, the universe undergoes a series of rapid expansions and contractions akin to the oscillations of a mechanical mixer or mixmaster, leading to complex and unpredictable behavior. The mixmaster universe is characterized by strong mixing properties, where spatial directions become intertwined due to gravitational interactions. This mixing results in a lack of uniformity in the universe's structure and properties, leading to anisotropic behavior. In the mixmaster universe, matter is evenly spread out, indicating homogeneity. However, it's not isotropic, meaning it behaves differently in different directions. You can think of an isotropic sphere as being uniformly consistent in all directions, whereas an anisotropic ellipsoid lacks uniformity due to differences along its various axes. Our universe is both homogeneous and isotropic, unlike the mixmaster universe. This suggests that the Mixmaster universe, if it existed, was only a feature of the early universe. It likely started anisotropic and quickly became isotropic over time. Charles Misner thought the Mixmaster universe could explain why the cosmic microwave background was so well mixed. This mixing couldn't have happened through ordinary forces because the parts that appear well mixed were too far apart for light to travel between them. It likely happened due to gravitational effects from the universe's expansion. Astrophysicists now believe that inflation caused the mixing by stretching out all the irregularities, similar to stretching pizza dough by hand. Inflation fits the data better. The Mixmaster universe is one of the solutions to Einstein's equations that has been proven to be chaotic. While chaos is understandable, proving it is difficult, especially in multidimensional systems. Most chaotic systems we know about are one- or two-dimensional, and proving chaos in multidimensional systems often involves reducing the problem to one- or two-dimension. Demonstrating chaos in a four-dimensional cosmology, such as the Mixmaster universe, was a significant achievement that evolved over many years and took considerable effort to resolve due to the unique challenges posed by general relativity. We often use chaotic to describe our lives as disorderly, but in science, chaos includes both disorder and order. The simplest way to find order in chaos is by looking at nature. If you examine tree growth, the shape of a mountain, or the formation of clouds, you will find both chaos and order together. Even though the individual examples may look different from each other, they show the same patterns. They are self-similar, commonly referred to as fractal. This means that no matter where you look or what scale you look at, the appearance of the structure will be the same. When you combine sensitive dependence on initial conditions with self-similarity, you get a phenomenon called a strange attractor. This is a complex concept in physics that creates unique, repetitive, and highly unpredictable patterns. These patterns are found in many natural and physical systems, including weather patterns and fluid turbulence. In science and engineering, understanding strange attractors can aid in designing systems that either harness or mitigate chaotic behavior. For instance, engineers might design control systems to stabilize chaotic systems in electronics or to understand the chaotic behavior in ecological models. A fractal is a pattern that repeats itself at different scales, creating a self-similar structure. As you zoom in on a fractal, you'll find smaller shapes that resemble the whole, and this process continues endlessly. Fractals are like patterns that replicate themselves, creating complex and unique shapes. They exist in dimensions beyond the usual width, height, and depth, including fractions called fractal dimensions. These dimensions help measure how complex a fractal is. The word fractal comes from the Latin word fractus, meaning fractured or broken. The concept was first studied closely by Benoit Mandelbrot in 1975. He described geometric fractals as shapes that can be divided into parts, each resembling a smaller version of the whole. Mandelbrot's work has been instrumental in helping us understand the origins and properties of fractals. Fractals might look complex, but they start from simple math and can be as basic as a line. You apply a rule, like removing the middle part of the line, and then repeat it on the remaining parts. This creates a fractal, like the Cantor set. The Cantor set is just one type of fractal. Fractals aren't just in math. They're all around us in nature, from blood vessels to galaxies. They repeat patterns on different scales, from tiny snowflakes to vast mountain ranges. These natural fractals aren't perfect copies of themselves, but still show fractal behavior. Why does nature use fractals? They're convenient. They let nature create complex shapes with simple rules and lots of repetition. This means nature can evolve biological and non-biological systems that resemble each other, using a set of basic rules over and over again. What stands out about fractals is their combination of simplicity and complexity. By applying a few basic rules iteratively, nature can create intricate structures that maximize efficiency in various processes. For example, fractal branching patterns seen in trees optimize the distribution of nutrients and sunlight throughout the organism. Fractals showcase profound simplicity within their intricate designs, adding vibrancy to nature. Despite the universe being mostly chaotic, there are points where transitions from chaos to complexity and order occur, often driven by external energy sources like the sun's influence on Earth, powering processes like photosynthesis and driving the Earth's climate systems. Within this energy-rich environment, molecules combined and evolved into complex organisms, creating ecosystems teeming with diversity. However, this order is temporary, as the second law of thermodynamics suggests that entropy, the measure of disorder in a system, tends to increase over time. Despite the temporary pockets of order that emerge, the overall trend in the universe is towards disorder. Eventually, all stars will exhaust their fuel and burn out. Scientific understanding often leads to philosophical questions. Even if the universe is completely deterministic and its future is predetermined, we cannot know the future with absolute certainty. We can only observe the universe's evolution. The universe itself cannot predict its own future. It functions as its own fastest simulator, continuously evolving in real time. Several reasons contribute to this unpredictability. The equations governing most systems in the universe are nonlinear. Minor changes in initial conditions can have significant effects on nonlinear systems. Even with precise measurements, there are inherent errors in determining initial conditions due to the limitations of physics laws and measurement technologies. Chaotic systems become increasingly unpredictable over time. These factors combine to make long-term predictions challenging, if not impossible, in many cases. Not far from chaos theory lies the strange and intimidating world of quantum mechanics. Quantum mechanics delves into the fundamental aspects of our universe, focusing on the behaviors of subatomic particles like electrons and neutrons in isolated systems. While it has practical applications, its theories often extend beyond our everyday experiences. It's not feasible to approach daily life from a quantum perspective, like saying, "I need a cup of quarks in opposing spin states." However, its concepts are essential for understanding patterns in physics and are often discussed in conversations about the universe. In quantum mechanics, a particle's possible states are called its quantum states. These states are described by the Schrödinger wave function, which determines the probability of finding a particle in a specific region at any given time in the future, based on its exact initial conditions. This indicates that the future state of the atom is entirely probabilistic. This is where quantum mechanics and chaos theory seem to encounter one another. What is the relationship between probabilistic outcomes in quantum mechanics and chaotic determination in chaos theory? When something is probabilistic, randomness is a factor for the predicted outcomes and is surprisingly highly predictable with percent chances. Whereas, as mentioned previously, chaotic determinism is not subject to randomness and not predictable. This seems extremely counterintuitive, but we must remember that the predictability of quantum mechanics only indicates the probability outcomes of the future state of particles, not the actual determined state. The wave function does not specify where an electron is, but rather shows where it is likely to be found. In other words, quantum mechanics is not certain, but rather highly accurate. And to reiterate, because the terms can get extremely confusing, probabilistic quantum mechanics inherently involves multiple potential outcomes due to the probabilistic nature of quantum states. It is not restricted to a certain outcome. In contrast, chaos theory is restricted to a certain outcome determined by initial conditions. However, while the outcome is determined by initial conditions and is not random, the extreme sensitivity to initial conditions makes long-term prediction practically impossible. A famous thought experiment in physics known as Laplace's demon considered the idea that if an extremely powerful entity were to know the exact initial conditions of every particle of the universe, the future could be entirely predicted. This changed the entire course of how people understood determinism and free will, but there were many crevices in the enigma. These philosophical topics will be saved for another time. For now, let's consider another example similar to Laplace's demon. Say we were investors with a deep understanding of quantum physics. If we could somehow analyze every single position and movement of every aspect of the current market, assuming such data could be precisely defined and measured, we might think we could maximize our future prediction accuracies. However, Due to the probabilistic nature of quantum mechanics, we could never determine the future market with 100% certainty. We could calculate the probability of a stock's value 5 years into the future, but we could never fully certify its exact value. The market is influenced by numerous factors and uncertainties, much like a quantum system. Even with extensive data and analysis, predicting the exact future values of stocks or market trends involves uncertainty. Analysts can estimate probabilities but not certainties. The study of quantum mechanics confronts a significant challenge when it comes to modeling real-world emergent phenomena. This challenge arises due to the inherent uncertainty of quantum mechanics, encapsulated in the Heisenberg uncertainty principle. This principle states that it is impossible to simultaneously measure a particle's position and momentum with perfect precision. There exists a trade-off between the uncertainty of position and momentum, with their product always greater than or equal to a constant value, where h is the reduced Planck constant. This means that it's impossible to know a particle's exact initial conditions in both position and momentum perfectly. Just as quantum mechanics faces limitations in predicting particle behavior, market analysts face limitations in predicting market trends due to inherent uncertainties. As a result, our hopes of mastering the market someday are dashed. Both probabilistic quantum mechanics and deterministic chaos theory lead to a similar conclusion. The emergent world can be described by mathematical systems, and these systems themselves represent the intricate patterns of the universe. Despite the challenges posed by uncertainty and complexity, these mathematical frameworks offer invaluable insights into the behavior of the world around us. The essence of everything we've discussed boils down to a profound concept: patterns. It's completely understandable if you're feeling a bit overwhelmed by the complexity of these concepts. Many of the mathematical theories we have today, whether describing order, chaos, probability, predictability, or determinability, challenge our basic intuitions. But that's the beauty of science. Physicists and mathematicians worldwide are continuously learning and refining our understanding of reality. The deeper we delve into these topics, the more we can appreciate the profound intricacies of our universe. Chaos isn't always just about challenges. It also reveals patterns in complex systems, shedding light on their true nature. Chaos is an essential part of reality that we can't ignore. It serves as a guiding light, allowing us to discern order within seemingly chaotic patterns and comprehend the intricate dynamics of the world around us. From the movements of celestial bodies to everyday occurrences like dripping faucets, chaos permeates all aspects of existence. By studying chaos, we can better understand our limits in measurements and uncover truths in unpredictability. And if we ever find a final theory that seeks to encapsulate the universe's workings, chaos theory's lessons will be a vital link. It reminds us that beneath life's complexity, there's simplicity waiting to be understood.